All right, so in this video, we're going to talk about Stokes' theorem. And Stokes' theorem is just a generalization of Green's theorem. And if you remember, Green's theorem allowed us to compute those line integrals over closed regions with one single integral, as opposed to having to come up with multiple setups and then adding their results together. So just as kind of a reminder here, Green's theorem, this was where we had the line integral f dot dr, and we broke it apart and showed that it was the pdx plus qdy dot product, which Green's theorem said, okay, we'll take closed region R and simply do a partial q partial x minus a partial p partial y dA. And so that was Green's theorem, kind of a reminder of that. Now, Stokes' theorem essentially is going to do the same thing for surface integrals now that we're in R3. We're going to let surface S be oriented, bounded, piecewise smooth with a positively oriented boundary curve C. And if that's the case, then we're going to be able to relate as a double integral over surface S curl dot n ds. Now, a couple things here. There's definitely a few things here to remember. First of all, the n ds we're going to refer to as the gradient of g dA. Additionally, this idea of curl is probably new to us. So let's go ahead and I'll define curl here. Curl is going to be the gradient cross f. Okay, so that's going to be a cross product. So I'll get this set up where we have our I, j, and k. And when we say gradient, it's very vague, as it should be. We're just going to do partial x, partial y, and partial z for the components then of that gradient vector. And then for f, traditionally we've used p, q, and r. So the result here being a vector, since we're crossing two vectors, we get a vector. And as we cross this, what we're going to end up with is partial r, partial y, minus partial q, partial z for the first component. Then we have partial p, partial z, minus partial r, partial x. And for the third component, partial q, partial x, minus partial p, partial y. And so when we talk about curl dot gradient g dA, it's going to be curl, this guy right here, dotted with the gradient of g dA to truly get that counterclockwise circulation that we mentioned back in Green's theorem. If you'll remember, there were a couple different formulas, and you can look on the handout. But this one in particular that we're going to show here in just a second was that counterclockwise circulation. And so that's what we're going to be allowed to find now using Stokes' theorem. All right, so I think it's somewhat important to show you guys the relationship between Green's theorem and Stokes' theorem to help better connect the two ideas. So if you remember, Green's theorem, I'm just going to say refers to R2. R2 meaning that we're dealing with some curves in a plane, which would mean that our n value, our normal vector, if we're considering, let's say, the xy plane, that would say that that n value could be our k vector, 0, 0, 1. So if we're in the xy plane, let's say, our normal vector could be 0, 0, 1, which is the k vector. So let's go ahead now and let f equal pq, as we've done before. But now we're taking it up into a higher dimension, into R3. We're going to need a cross product, so therefore we're going to need that third component. So we're going to use pq0. And if I compute the curl of f, which is going to be that cross product, I, j, k, we'll have partial x, partial y, partial z, and then we'll also have our p, our q, and our 0. So if we run this calculation now, we're going to get negative partial q over partial z. We're going to get partial p, partial z, and then we're going to get partial q, partial x, minus partial p, partial y. So that's that simple cross product there. Now, as we discussed, we're looking for the curl of f dot n. Well, our n is going to be the k vector. So if I take this now and I dot it with 0, 0, 1, you can pretty clearly see that all I end up with now is going to be that partial q partial x minus partial p partial y. And so there sits that integral now, dA, that was Green's theorem. So using Stokes' theorem, we were actually able to kind of reverse engineer Green's theorem. And again, it just shows you the relationship they have between the two. All right, so in this example, we're going to take a look using the vector field f here, and our curve is going to be the triangle in the plane z equals 1/2 y with these vertices. Now, it'll be given in all of these problems. I'm going to write on here counterclockwise orientation. Nothing assigned will be different than that, so just assume counterclockwise orientation, so this thing will work out nicely. So first thing I'm going to do, I'll go ahead and compute the curl of f, and so that's going to be where we have our cross product, I, j, k, and if you'll remember, that's nothing more than partial x, partial y, partial z, but now with a negative 3y squared, a 4z, and a 6s. So I went ahead and plugged those guys in down there. And so you can certainly work this out from scratch if you want to. You can use the expansion from the very first part of this video if you'd like. It's completely up to you how you compute this. But at the end of the day, this ends up with as a negative 4, a negative 6, and a 6y. So next thing we'll need is our g. Remember, what we're shooting for is curl of f dot gradient g. So for g of x, y, z, that's going to be, much like we did in the last couple sections, z minus 1/2 y. And then that gradient of g would be a 0, a negative 1/2, and a 1. So if I take this now, again, curl dot gradient g, if I go ahead now and dot those two things, maybe I'll just set that curl over here. So that's going to be negative 4, negative 6, and 6y. And in dotting these, we'll get a 0 for the first one. We'll get a 3 for the second one, and then a plus 6y for the third one. So this will give us 3 plus 6y. All right, so I'll go ahead now and drop that in, 3 plus 6y. And then we just need to focus now on our region. We're going to have a combination of dy dx or dx dy over here, but again, that's going to be dependent upon what we're dealing with now in R2. So if I take this, I know that I have the surface here with these vertices. So now I'm going to project this into R2. And if I project this into R2, this vertice is going to be 2, 0. This vertice is going to be 0, 2. And again, I'm getting that from looking at, well, essentially I'm doing this. I'm ignoring the z right here. If I ignore those z's, then I'm getting my 2, 0 right there, my 0, 2 right there, and then my 0, 0, which would put me right back here. So this is going to now be my region here that I'm going to be interested in studying. So when I come up with the equation of that line, that's going to give me y equals 2 minus x. So it probably makes sense now to go dy dx, where our y is going to range between 0 and 2 minus x, and our x value now is going to go from 0 to 2. So 0 to 2. And so there's your setup on that one. And remember, the really only different thing, the only different part to this is the fact that now we're computing this curl as a cross product. So again, I would encourage you to go back and take a look at the first slide just to make sure you're comfortable with how everything works in terms of these partial derivatives being affected on these components from the vector field.